Okay, guys, today we're talking about the graphs of the other trig functions: tangent, cotangent, secant, and cosecant. So let's graph one period of the tangent function, the basic tangent function. Just like I did yesterday, we're going to go through one period of the tangent function, the basic tangent function, and then show you how to adjust it if you end up multiplying outside of the function by something, or the x by something, by a constant. I'll show you how to adjust your scaling. But that's going to be the name of the game. It's going to be basically the same picture every time, perhaps the inverted version of the picture if there's a negative out in front, and then adjusting the scaling. That's the quick way to graph these by hand, which is what I want you to know about. So the tangent function, there are 3 points that are handy to plot here. 3 points. What are they? So x comma y equals tangent of x. Now we're graphing one period. One value that's handy to plot for x is 0. You'll see why in a second. The other value is pi over 4. Why do you suppose that is? What's the tangent of pi over 4? It's a nice value of 1, isn't it? So it's just, you get a nice, easy value to work with when you plot pi over 4. And then on the other side, how about negative pi over 4? Which turns out to be negative 1. So yeah, we get negative pi over 4, negative 1 on the graph. What's the tangent of 0? 0. And tangent of pi over 4? 1. So those 3 points are handy to plot, or the equivalent of those 3 points when it gets scaled differently. And I'll show you how to figure out what the x values turn into in that case. So let's graph a picture of this, and then we'll talk about domain and range and all that fun stuff. So let me get an axes here. Here we go. X, Y as usual. Do you guys remember what the tangent is in terms of sine and cosine?
It's cosine, it's sine over cosine.
Yeah. So unlike, you can write it as a fraction, right? A non-trivial fraction. So unlike sine and cosine, there's going to be certain values that you can't plug in. Certain x values you can't plug in. Why?
Because they do not exist.
They're going to create 0 in the denominator, right? Right? So in fact, any x value that makes the cosine of x 0 means division by 0, and that's not going to be in the domain of the tangent, right? So what values make the tangent undefined? Same values that make cosine 0. What are those values? Well, there's lots of them. There's an infinite number of them, but which ones will we concentrate on? What's the first positive one?
Pi over 2.
Pi over 2. So I'm going to plot, okay, not on the graph, but on it's not part of the graph, but it's going to help me as a tool to graph this thing. I'm going to plot the x value of pi over 2, but in the form of an asymptote. Does everybody see why? So this is called a vertical asymptote because any x value on this line has value pi over 2, I'm going to say. And so as the equation of this line would be x equals pi over 2, pi halves. Because any ordered pair on that line, the x value is pi halves, right? And what I'm saying is the graph of the tangent better not cross that. Because when x equals pi halves, you get division by 0. So you have to have a vertical line there that the graph doesn't cross. We call it a vertical asymptote. Sound familiar?
Hyperbole?
What's that?
Hyperbole.
Yeah. Some hyperbolas have asymptotes as well. Not necessarily vertical, but yeah. Now there's another one. There's an infinite number of them, but there's another one at negative pi over 2, right? So think about it. The cosine of negative pi over 2 is also 0. So I'm going to throw in that asymptote as well and say, hey, the graph of the tangent's never going to cross there. And the one period that we're going to graph is the one in between the asymptotes that goes through 0, 0. Okay, so in fact, if you plot these 3 points, you'll have a really good idea then, along with the asymptotes guiding you, you'll have a really good idea of what this graph looks like. So let's start with 0, 0. And then, of course, if this value is pi over 2, where's pi over 4 at? Right between the y-axis and the asymptote, right? So that's what made it a nice value to plot. And same with negative pi over 4. Okay, and then I'll put a 1 here. So 1 there, and then negative 1 down here. Okay, so then when we plot these values, 0, 0, I already plotted. Pi over 4, comma 1 would be up here. And negative pi over 4, negative 1 would be right about here. Now, if you're not careful, you're thinking that looks like a straight line, right?
Isn't.
Can't be, right? Because it's not going to run into the asymptotes. So what happens is, as you go to the right, towards the right-hand asymptote, the graph goes up and it just gets higher and higher and higher as x gets closer to the asymptote. Likewise, as you go to the left from the origin, the graph goes down and it gets down to like negative infinity eventually. Well, it never gets there, but it goes towards it. And so you get a graph that looks somewhat like this. It's got a nice, gentle curve in the middle. Actually, I probably curved it a bit too much, but that's okay. So I'll draw it like that. Yeah, I curved it a bit too much there. And so if you didn't make it through the point, just make the point bigger, right? That's the rule? Yeah? You guys have never used that rule before? Okay. So what I'm trying to show here is that as you go from 0, 0 to the right, it just goes up and up without bound as x approaches pi over 2. And as you go from x equals 0 to the left, the graph goes down without bound and approaches, well, it goes down without bound as x approaches negative pi over 2, I should say. And then there's your graph. Now, I could clean this up a little bit. If you didn't like my idea of just making the point bigger, I can make it look a little bit better. But it wasn't that bad to begin with. Okay? Does that look familiar to you? Not so bad, right? Every time you meet a new function, you shake its hand and you say, hey, what's your sign, baby? No, you don't do that. What do?
Domain.
You say, what's your domain?
All your numbers. Negative.
So take a look at that picture. Let me squeeze this together a little bit. Now, one thing I should emphasize is this picture repeats over and over again. This is just one period, right? But by the way, keep in mind the period of the tangent function is what? Pi, which is exactly the distance between the asymptotes, negative pi over 2 and positive pi over 2, right? So we graphed one period of this. This picture repeats itself over and over again as you go to the right and as you go to the left, as do the asymptotes, right? With a distance of pi between the asymptotes. So you can't just say the domain of one period is between negative pi over 2 and pi over 2. The main period, that's the domain. But what's the domain going to be overall? We're just going to have to exclude an infinite number of values, right? Well, I think we can see a pattern. If we just extend this graph a little bit, I think we'll be able to see a pattern fairly quickly, in fact. So let's extend the x-axis a bit. Let's go over a distance of pi. That's from pi over 2. Let's go over a distance of pi. So about this distance here. And I'm just eyeballing it. And that'll get you to your next asymptote, which will be what? If you add pi to pi over 2, what do you get?
3 pi.
Yeah. Everybody see where this... So the equation of this line is x equals 3 pi over 2. Does everybody see where that comes from? The period of the tangent function is pi. And the graph itself, the occurrences of this typical curve, this repeating cycle, happen between the asymptotes. So the next asymptote is going to be pi units, the period, in this case, the period, away from the last asymptote. And so we're going to get, I'm not going to take as much time here, but it'll cross the x-axis right in the middle like it did here, and of course be just a copy of the last graph. Okay? Now, if I had room, where would the next asymptote to the right be? At x equals, if you added pi to 3 pi over 2, what would you get? So just think 2 pi over 2, that's pi, plus 3 pi over 2, 5 pi over 2 would be the next asymptote. And if you went the other way, the next asymptote, if you subtracted pi, if you went a distance of pi the other direction, where would this asymptote be? So again, this distance is still pi. It would be at negative 3 pi over 2. So, so you can see it in the video. There you go. Negative 3 pi over 2. So what's the pattern? What kind of x values are excluded at each asymptote from the domain is what I'm trying to get at. And what's the pattern? What kind of x values are we excluding? Well, there's got to be a way to say it symbolically so that we can encompass everything at once, right?
You say pi over 2x.
Well, we wouldn't want to use x, right? Because that's the value we're using for the input. But I see what you're saying. You're on the right track. It sure looks like, now let me write this a different way. I could write this as 3 times pi over 2. 3 pi over 2, couldn't I write that as 3 times pi over 2? Would you buy that? And then 5 pi over 2 is way over there. Couldn't I write 5 pi over 2 as 5 times pi over 2? And couldn't I write negative 3 pi over 2 as negative 3 times pi over 2? And then here we have, couldn't we think of this as 1 times pi over 2? And couldn't we, and we could think of this one as negative 1 times pi over 2. If you went further to the right, another asymptote would be at 7 pi over 2, 7 times pi over 2. What kind of numbers are like 1, 3, 5, and 7? Odd. So it sure looks like to me that the domain is going to be all reals except odd multiples of pi over 2. Does that make sense? Okay, so now we're getting mathematical here, right? That's the idea. We want to express common everyday language into a nice condensed form that makes sense, that everybody can read. It's a universal language, right? So, and that takes time to develop that skill. So we'll talk about that. Now, the period we know is pi. The domain, okay, we could write it out. Odd multiples, let's see, all reals except odd multiples of pi over 2. All real numbers, all reals will say, but odd multiples of pi over 2. But there's got to be a better way, right? More symbolic. I mean, that's kind of clunky language. It's not clunky, but it's long, right? That's the beauty of symbolism. You can say a lot with a little. So let's see. I think probably the easiest way would be to use what we call set builder notation here. So, and set builder notation becomes really important later on. So let me remind you of set builder notation. In set builder notation, we could say this. Curly bracket for set, right? Okay, what kind of input is, what's our input variable? X. Do you remember what the vertical bar means?
It's supposed to denote everything within that set.
Yeah, that's true. Usually we translate it to the phrase such that, okay, right? Vertical bar translates to the phrase such that. Such that, okay. Now the assumption is x is a real number, so we don't have to write that down. Unless you're told otherwise, the assumption is x is real. So the set of all x, all we have to write down is the restriction, such that x does not equal, well, okay, it's going to involve pi over 2. How do we write a generic odd number? How do we write a generic even number? So numbers like 2, 4, 6, 8. Who do we appreciate? Mr. Chamberlain, no, okay, 2, 4, 6, 8. I can see you guys are very serious today. 2, 4, 6, 8 even numbers. How do we express even numbers? What do they all have in common? A factor of 2. So an even number can be expressed as like 2 times k, where k is not just a counting number, but an integer, right? It could be a negative counting number, or it could be 0. So 2k, where k is an integer, can represent any even number. How do you make it an odd number? How about you subtract 1 from it? So if you say 2k minus 1 quantity times pi over 2, that's a symbolic way to say all odd numbers, as long as you make it clear what k is. K, an integer. And if it's understood that k is an integer, you can leave off that last part, and it becomes fairly compact. So right now you're saying, I like the part in black better, but symbolically it becomes convenient to use this language, especially when it becomes more complicated than that. So both the phrase in black and the phrase in green, the mathematical symbolism in green, are ways to express the domain. Make sense? Okay, go back to the picture. The range. What's the range?
Negative infinity, positive infinity?
Yeah, it goes all the way down, all the way up. And I think interval notation is the most convenient notation to write that. And so we're contrasting set builder notation. This is set builder notation. Usually interval notation is easier to use, but interval notation would have been awkward here, I think. You could probably figure out a way to do it, but it would have been awkward. So just interval notation for the range is easy. It goes all the way down, it goes all the way up, negative infinity to infinity. Okay? Now we're going to graph y equals cotangent x in a very similar way to how we graphed y equals tangent of x. What's the trig identity you remember about cotangent in terms of sines and cosines? So it's cosine over sine. And so we're going to have asymptotes here as well, right? Where, what x value makes sine 0? What's the first one that you usually think of? Sine of what equals 0?
0.
Sine of 0 equals 0, yeah. And then what's the next one? You know what a neat trick is?
Pi.
Yeah, pi, yes. You know what a neat trick is? If you have the graph of the sine function memorized, which you will eventually if you don't already, you can actually see where the x-intercepts are of the sine function, and that's where the sine's equal to 0, right, at the x-intercepts? The height value is 0. So you can actually see where it's equal to 0 visually if you have this graph in your head, which you will. And so, I mean, obviously it doesn't stop here, but the first non-negative one is 0. And then, oh, we know this value is pi, if this is just y equals sine x, that is. And then the next one is 2 pi, right? What's the next one? What would the one be over here? 3 pi. What would the one be over here if I continued the graph on like that? What would the one be over here? Negative pi, negative 1 pi if you like, right? This would be positive 1 pi. So what's the pattern? What kinds of values of pi? Just multiples of pi, right? Even and odds, right? Yeah, so that's going to be helpful. So that picture, if you have that picture in your head, you can figure things like that out rather quickly. Okay, so let's graph this thing. Again, we're just graphing one period, but when I state the domain and the range, I'm talking about the entire graph, right? Okay, so 3 values I'd like you to plot here. Not the same 3 as for tangent. A good one here, well, okay, we can't plot 0, can we? Because x equals 0 is actually an asymptote, isn't it? But what's the period of this thing? So I'm trying to indicate that's an asymptote. What's the period of this thing? What's the period? Pi. And as we've already noted, if you tried to plug in pi and take the sine of it, you get 0, you get division by 0, right? So there's an asymptote there as well. So just like before, I'm going to plot the 2 asymptotes. The y-axis is an asymptote, and the line x equals pi is an asymptote. Obviously there's a lot more, but I'm graphing just one period, and these are typically the 2 asymptotes we draw for one period. And then you're going to want to plot the value in between the asymptotes, this value, which would have to be what? Pi over 2, and then just split that value in half. Plot pi over 4, And then split the value between pi over 2 and pi in half. What would that be? 3 pi over 4. So those are the three values or kinds of values you want to plot here. This interval, the first interval represents 1/4 of the period. And then between 1/4 and 1/2, between 1/2 of the period and 3/4, between 3/4 and 1. So those are the kinds of values you want to plot. Now, those values themselves change depending on what you're multiplying the x by, right? But as far as the relationship between the values and what part of the period they take up, that doesn't change. Okay, what's the cotangent of pi over 4? What's the cotangent of pi over 4? Well, what's the tangent of pi over 4? 1. So what's the cotangent? 1. Now, what's the cotangent of pi halves? Okay, use this if you're not sure, right? What's the sine of pi halves? It's 1, right? What's the cosine of pi halves? 0. So what's the cotangent of pi halves? 0 over 1 is just 0. So if you forget, you can get it. What about 3 pi over 4? Cotangent, rather, of 3 pi over 4?
-1.
It's going to turn out to be -1. Okay? And you can always verify that. If you know your cosines and sines, you can always verify that by plugging into cosine x over sine x. Well, now, once you know that, it's not that hard to plot. Okay, we're going to have to go up to a height of 1, -1. Well, we go actually a lot further down than that, and a lot further up than +1, but those are the ones we're plotting. So pi force over pi force up 1. Pi halves is an x-intercept, right? Pi halves 0 is an x-intercept. 3 pi over 4 is at -1. And then you just use those points and the asymptotes as a guide, right? As you go to the left, does it look like the graph is going up as you approach the y-axis from the left? It's going up. So if I draw it, as you go from the left the other way, it comes down. And it swings around in a nice smooth curve. It's not a straight line. And then it goes down as you go to the right. And if you want a more accurate graph, what can you always do?
More points.
Plot more points. That's all your calculator does. Your calculator's not very smart. It's not artificially intelligent, right? All it does is plot points really quickly. So you are smarter than your calculator. Okay? Makes sense? All right. So now let's shake the function's hand and ask it, hey, what's your period? But we already know that, right? We know the period is pi. Now let's think about the domain. Again, I'll use set Builder notation, the set of all x such that it's assumed x is real, so we don't write that down. So we just write down the restrictions. So go back up. Well, I kind of erased the graph of the sine, but where are the x-intercepts of the sine function when you graph it? In other words, when is the sine function equal to 0, height-wise? At multiples of pi. We already saw that. So those are the values we actually have to restrict, because those are the values that make the denominator of cosine x over sine x 0. Cosine x over sine x is cotangent x. So though undefined, right? Can't divide by 0. So multiples of pi we restrict. So how do we write multiples of pi? X cannot equal multiples of pi. We just say x cannot equal k pi. Sorry, I had a 2 in there, and that's not right. It's k pi, where k equals an integer, right? What are integers? They're values like counting numbers, 1, 2, 3, 4, 5, blah, 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 but 0 and the opposite of the counting numbers, -1, -2, -3, blah, blah, blah. Make sense? Okay. About the range. Look at the graph. How low does it get? How high does it get? It goes all the way down, all the way up, and everything in between, right? Because it's a nice continuous graph. So it's probably, and I'm just, for convenience, I'm switching notations here. Interval notation, -infinity to infinity. So hopefully that doesn't throw you off, okay? All right, the next two, easy peasy. if you know the graphs of the sine and cosine. So the secant function. There's a trick to remembering how to graph the secant function. There's going to be a helper function with it. The helper function, you're going to set y equal to, the cosine of x. And how are these guys related? They are reciprocal functions. So that's how you remember. You set the helper equal to y equals cosine of x, and remember, oh yeah, they're reciprocals, right? So why does that help us? Well, it helps us determine when we graph the cosine of x, the x-intercepts of the cosine of x, much like with the tangent, it helps us determine where the asymptotes are. And it also helps us determine where the kind of the minimum values, the relative minimum and relative maximum values are of the little sections of graph you get in between the asymptotes. So here's how you do it. Okay, so we discussed it a little bit ago. Tangent of x is equal to sine over cosine, and we decided that the intercepts, the places where the height of the cosine function is equal to 0, that's where the asymptotes are going to be. Let's graph the function, and it'll be immediately obvious where those points are. So I'm going to start off at a height of 1. I'm just graphing one period. If we need more than one period, you could extend it a little bit. If you need lots of periods, you could graph it on a calculator. And remember what the cosine function looks like. You start at, I'm going to do this as a dotted curve. You start at the maximum height. It goes down, hits the x-axis, goes down to the minimum height, and then back up again. That's the part of the wave that you graph. Right? And so you're essentially plotting these 5 points. This guy, the intercepts, the minimum value, and the maximum value. Corresponding to the hash marks 0, whatever this guy is, whatever that guy is corresponding with that minimum, that guy and that guy. And so what's the period then of the cosine? We know that that's 2 pi, which makes this hash mark 2 pi. Makes this one pi. Just like yesterday, cut pi in half, get pi over 2. Halfway between pi over 2 and 2 pi is 3 pi over 2, which is actually the 3/4 mark of the period. So the secant of x has a period of 2 pi too, same as its reciprocal function. Now draw asymptotes corresponding with the x-intercepts, because those are the values. Since the secant of x is equal to 1 over cosine of x, those x-intercepts correspond to where the secant's not defined, so they correspond to vertical asymptotes. So just draw vertical lines through x equals pi over 2. Got a little off track there. And label it. It is an equation, right? X equals pi over 2. And also 3 pi over 2. Like so. Label it. It's an equation. This is the equation of that vertical line, x equals 3 pi over 2. And it turns out that if 0, 1, so check out this point right here. If 0, 1 is on the graph of the cosine function, it's certainly on the graph of the reciprocal function, right? So this point's actually on the graph of the secant. And if you plot a few more points, you'll realize that as you approach this first asymptote, you get a U shape. Well, half of a U shape, because we're only graphing one period. But if you graph the whole period, you'd get a shape that looks like, if you graph more than one period, you get a U shape. So this section of it between the asymptote to the left of the y-axis and this asymptote to this first asymptote to the right of the y-axis is a U shape. But if you only graph one period, then that stuff in lavender there you don't see. Whoops, went too far. So I'm trying to graph that portion of it. And then in between the asymptotes, corresponding with this minimum value, this negative 1, if pi negative 1 is on the graph of cosine of x, certainly it's on the graph of secant. And then you get kind of an upside down U shape. If you plot a few more points, you can convince yourself you'll get an upside down U shape in between the asymptotes. And as you go to the right, it goes down forever and ever and approaches this right-hand asymptote. As you go to the left from the point pi negative 1, it goes down forever and ever and approaches this asymptote to the left. Then over here, if the point 2 pi comma 1 is on the graph of cosine, certainly it's on the graph of secant, and you'll get half of a U shape. The other half exists, it's over there, but if it's over here, but if we're only graphing one period, it doesn't get plotted. Okay? So don't think that's what it really looks like. What it really looks like is a U shape. Let's see, from your perspective, a U shape, an upside down U shape. As you go to the right, you're right. Then another U shape, another upside down U shape, and so on and so forth forever and ever and ever and ever. Okay? But the idea is, if you can graph that helper function, the cosine of x, you can remember the stuff in purple, right? The secant function. That's not too bad, is it? Okay. Let's go ahead and talk about the period. Same as its reciprocal function. So it's going to be 2 pi. So all you have to remember is this. Tangent and cotangent have what period? Pi. The rest have period 2 pi. The rest of the trig functions have period 2 pi. So 2 pi is the period. The domain, it's going to be the same as tangent. So I'll let you see what we did previously. Because the denominators, when you write in terms of sine and cosine, the denominator of the tangent function is cosine of x, right? Denominator, when you write in terms of sines, or in this case cosines, the denominator is the cosine function. So the domain it has the same asymptotes as the tangent function. The range, this is interesting. It goes from negative, if you think height-wise, negative infinity is down here somewhere, right? Negative 1 is right here. That would be one interval in the range, right? And then from 1 right here all the way up to, on the y-axis, positive infinity is up here somewhere. So we could combine those two intervals together and say that the range in interval notation is negative infinity to 1. Does it include 1? Negative 1 is what I meant, yep. Negative 1, does it include negative 1? Yes, it does. Then union, what would be the other one? 1 to infinity. Yep. So that's a nice way to write it. If you're not comfortable with interval notation or set builder, get comfortable with it. And then there won't be that language barrier, right? The jargon barrier, I like to call it. Jargon, half of what's hard about math is the jargon. Because math, a lot of math is just common sense with jargon applied. The last of the basic trig functions. Y equals cosecant of x. Guess what? The trick is going to look awfully similar as for graphing y equals cosecant of x as it did for secant of x. What's the helper going to be?
Y equals sine of x.
So your helper function is going to be y equals sine of x. What's the relationship between the two?
Reciprocal.
They are reciprocal functions. So the intercepts, the x-intercepts of y equals sine of x essentially give you the placement for the asymptotes of y equals cosecant. Does that make sense? That's why we use it. And it gives you a couple of points in the graph as well. So sine function, 1 period. There's 1 hill. There's 1 valley. Good enough. Okay, if it's just a basic sine function, what's the period? 2 pi. So label this scale mark 2 pi. Split it in half. Split that in half. Split the scale marks between pi and 2 pi in half. So same sort of scaling as before. And then so we're essentially plotting these points. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0. So 1, negative 1. It is that easy. I feel like I'm selling you a food processor. Is it really that easy? Yes, it's that easy to graph the sine function. One period of it, anyway.
There's more.
But wait, there's more, exactly. So where are the asymptotes of its reciprocal? Or of the reciprocal, yeah, I said it right, of the reciprocal, which would be 1 over sine of x, or cosecant.
Or it crosses the x.
Wherever these intercepts are, right? So you can draw in the asymptotes. One of them is going to be right through the y-axis, isn't it? And then where else? Going to the right. Pi. I just say that automatically now. Sorry if it's getting on your nerves. And then 2 pi. And then certainly if pi over 2, 1 is on the graph of sine of x, you take the reciprocal of 1, right? It's that same point will be on the graph of cosecant. Reciprocal of 1 is 1. But then you're going to get, if you plot a few points, convince yourself, you'll get this kind of U shape that approaches the respective asymptotes as it goes to the left and right. And then here, if 3 pi over 2, if the y-coordinate of -1 is a y-coordinate of, or is a value of sine of x, certainly it's a value of cosecant. And then it goes down from here. So it really is the same shapes that make up the graph of the cosecant. They're just placed in a different spot horizontally. Okay? The period we said was 2 pi. Domain would be the same as what? Since the denominator of the cosecant is sine of x, the domain would be the same as cotangent. So I'll let you look at that. The range is actually the same as what? Same as secant. So I'm kind of cheating, saving some time there. Okay, so let's graph one full period of y equals 3 tangent 2x. And you know, mathematicians are lazy. They try to find the sneakiest, maybe not the sneakiest, but the most clever way of doing something, oftentimes anyway. And my clever way of doing this is I'm going to graph you the same picture as y equals tangent of x and adjust the scaling. So here I go. So what were the critical pieces of information we used to graph y equals tangent of x, that first example? We needed what, first of all? It wasn't actually part of the graph. We needed the asymptotes, okay? So for the tangent of x, the main period that we plot for the tangent of x or some variation of that, we graph the period that has the y-axis in between the two asymptotes. And then the two asymptotes are the same distance from the y-axis on either side. So that's something that you can grab a hold of and remember. So one asymptote would be to the right some distance. We'll talk about what that distance is in a second from the y-axis. And the other asymptote will be the same distance. So I'm trying to make these scale marks look exactly the same. And then I'm going to draw vertical lines between them. Dotted because they're not actually part of the graph, are they? They're not actually part of the curve that represents one period of this tangent function. Okay. And then there's 3 points I like to plot. Now in this particular case, the period's not going to be pi anymore, so I don't know what this scale mark is, but I do know it should be halfway between the y-axis and the right-hand asymptote. Likewise, this scale mark should be halfway between the y-axis and the left-hand asymptote of the main period. And then we have a number, a value we plot on the y-axis, and then positive, and then a value negative, same distance away. And so we end up plotting these points. Same as before, what's changed is the scale, so the value of the coordinates of those points are going to be different. We'll talk about that in a second. Now, the picture I draw, though, is going to be this, very, very, very similar to the first picture. And, well, you know what? I do better if I do it from the left. So I'll go this way. It curves ever so slightly through the origin and then up. And you can see the curve a little better if you make the asymptotes a little closer together. But anyway, there you go. Okay, so then I got to be honest with you. I was lazy here. I didn't do anything different than I did in the first example as far as graphing this thing goes. So now we have to find the period and then label appropriately. Okay? So what's the normal period of the tangent function? The normal period is pi. Now I haven't given you a formula for finding the period of 3 tangent 2x, but based on what we did with cosine and sine, and based on how a horizontal stretch or shrink works, what would it be? Pi over 2, whatever the number is right there. What does that mean? That means the entire distance between the asymptotes. So this is worth knowing. The entire distance between the asymptotes is pi over 2, which means half that distance out to this scale mark here is what? Pi over 4. So the equation of this asymptote is it's a vertical line. Vertical lines always have the equation x equals a constant, and in this case pi over 4. X equals pi over 4. And what would the equation of the left-hand asymptote be? Negative pi over 4. And then that's almost the whole ball game, right? Because you can get the other scale marks based on the horizontal placement of those asymptotes. So what would this middle scale mark be? It would be
Pi over.
It would be half of this, so pi over 8. And then this would be the opposite of that, negative pi 8ths. And then what would this value be right here? So this is what we were talking about. Somebody asked me about the amplitude. It's not the amplitude, but this pi over 8, this number that splits the y-axis and the asymptote in half, is the number you could plug into the function, and when you take whatever number here is here, in this case 2, times that, 2 times pi over 8 is what? This pi force, and that's the number that makes the tangent 1 when you plug it in. So whatever this value turns out to be, in this case pi 8ths, every single time you plug it into a function of the form a tangent bx, that's the value that's going to make the tangent 1, and then the actual height value will be, it'll be 1 times whatever this value is out front. So it's at a height of 3. The tangent function is at a height of 3 when you plug in pi over 8 midway between the y-axis and the asymptote. And so some people like to create an analogy with that in the amplitude, although it's not an amplitude. And then if this is 3, what would this negative scale mark be? Negative 3. And there you go. Okay, so I won't be nearly as detailed, but I do want to show you guys this so you have it for your homework. What's the helper?
Cosecant. Sine of x.
Y equals sine of x. Now notice I deleted the negative. So eventually I'm going to have 2 helpers, helper 1 and helper 2. I'm actually, at some point, I'm going to want to plot y equals negative sine x. If you wanted to just jump to y equals negative sine x, that'd be fine. But I'm going to graph a couple of helpers. And it will make it a little bit messy, but that's okay. So my first helper, just sine of x. Like that. Made it a little too long for my axis, but that's okay. And then what does the negative do?
Flips it.
Flips it. So let's see, this is here and here. So the negative out in front inverts the graph. So in green, I'm going to graph this guy in green. Y equals negative sine x. So should hit this point. And I went way too far down with that scale mark. Actually, what I did was I went too far down with that, but oh well, we're in a hurry. So this point stays the same, but this guy goes down here. This guy stays the same. This guy goes up here, and any x-intercept stays where it's at. So the function in green is your main helper function. Make sense? Okay, asymptotes. We've got the y-axis, which has the equation x equals 0. What's this one going to be? X equals, well, actually, we need to figure out the period, and I'll mark them in a second. And then this one. Usually I do them dotted, but I'm in a hurry. Okay. And so what does the graph look like? Focus on the helper in green.
Left parabola is pointing downwards.
It's not a parabola, because parabolas don't have asymptotes, but it does look like a parabola. It's like downward U shape, I guess. And then here is the upward one. And then you just have, whoops. Once you have that, you just have to work out the scaling, guys. So what's the period of this thing going to be? It doesn't, now, I got in a hurry here. I got a little bit sloppy. I mean, I could have done it that way, but really, you want to include the same argument with your helper functions. Okay, so you can look, to get the period, you can look at this or at this. It's going to be the same formula. And say that the period is 2 pi over whatever number is out in front of the x in either equation, right? So 2 pi over pi, which is 2, which makes this guy 2 right here, or the asymptote x equals 2. And then this guy must be x equals 1. How high does it get? What's the amplitude of your helper function? Yeah. So again, I got a little sloppy here. I could have kept the 3 in front, and then the amplitude is there for you to see, and it is the absolute value of -3. And so this, long story short, this scale mark on the y-axis is 3. This one is -3. The graph in lavender is the graph you're looking for.